Hi, I'm Jennifer Gonzalez, and today we're going to go through a coherence portion of the Launch Eureka Math PD. To start, we're going to be in a story of units. Here, we're asked to use a model to multiply 15 times 13. The model I'm going to use is called a rectangular array. I'm going to start with a rectangle and split it up into sections 10 and 5, and then 10 and 3. Now let's discuss why I chose the numbers 10, 5, and then 10, 3. Well, as you may see, 15 equals 10 plus 5, and 13 equals 10 plus 3. This is something that students build an understanding earlier in a story of units using the unit cubes as well as tape diagrams. So students recognize that they can rewrite 15 or 13 using a model of 10 units and 5 units. So building off of that knowledge, we are going to use a rectangular array to help us multiply 15 times 13. We also are engaging that prior knowledge of area, where students know that the length and the width multiplied finds the area of a rectangle. So we're going to find the partial products of each of these sections and then find the sum of those partial products to find the total area of the entire rectangle. So let's get started. 10 times 10 is 100. 5 times 10 is 50. 10 times 3 is 30. And 5 times 3 is 15. Now, in order to find the total area of this rectangle, and therefore finding the product of 10 plus 5 times 10 plus 3, I have to add all these partial products together. Therefore, I'm going to do 100 plus 50 plus 30 plus 15. Altogether, we get a sum of 195. This means that 15 times 13 is equivalent to 10 plus 5 times 10 plus 3, and therefore is equivalent to 195. This helps build the foundation of the distributive property as students move into a story of functions, which leads us into our Algebra 1 example. In a story of functions, beginning in Algebra 1, students are now asked to use a tabular method to multiply polynomials. In this example, we're going to multiply x plus 5 times x plus 3. Let's discuss some similarities and some differences. If we look at the two models, we can see that they're both set up nearly the same. They're both using a rectangular array. We have just now decided to call the rectangular array a tabular method, as it is more friendly to our negative lengths. We also are now using variables. Rather than in our previous example, we used whole numbers. Now, instead of 10 plus 5, I have x plus 5. And instead of 10 plus 3, I have x plus 3. However, I'm still going to use the same method to multiply each of these sections and add the partial products in order to find my ending product of these two polynomials. So let's get started. I'm going to do x times x, which is x squared. Then I'm going to do 5 times x, which is 5x. I'll also do x times 3, which is 3x. And then lastly, I'm going to do 5 times 3, which is 15. Again, just like we did in a story of units, we added all these partial products up to find our ending product. However, here, we can only combine partial products that are considered like terms. If you look at this model, where are your like terms at? Well, assuming you did it all correctly, we can show our students that the partial product should lie in each diagonal. So for example, x squared has its own diagonal of x squared. However, 5x and 3x create a diagonal of 8x. 5 plus 3 is 8, and then your like term x. And then 15 is in its own diagonal of 15. So the sum of our partial products shows us that the product of the quantity x plus 5 times the quantity of x plus 3 will result in x squared plus 8x plus 15. Now, when our students move on to Algebra 2, we take it a step further. Rather than multiplying our length and width, we're actually going to go backwards and we're going to find the factors. So in this next example, we're going to use the tabular method to factor x squared plus 2x minus 15. So remember, our tabular method is set up like a rectangular array. We're just using a different name now. And now I start off with x squared plus 2x minus 15. So as you can see, we're starting with a product now. Well, if we look at our previous example, where is our ending product at? Well, it goes with each diagonal here. So we have x squared, we have 2x, and we have negative 15. So now I would like to find the length and width of each section in order to create x squared plus 2x minus 15. We're just going to work backwards. So if we look at our previous example, you can see that x squared was obtained by doing x times x. Well, that still holds true here. X times x will still get me x squared. Well, next, we see that 15 in our previous example here came from that bottom diagonal. So I know that this bottom box here needs to be negative 15. So that means that these two blanks here must multiply to get negative 15. Well, we actually have quite a few possibilities there. So in order to multiply to get negative 15, I could do 1 times negative 15. I could do negative 1 times positive 15. I could do positive 3 times negative 5. And I could also do negative 3 and positive 5. So we have quite a few options here. Well, still, from Algebra 1 and our previous example, we know that whatever numbers we pick to multiply to get 15, when they fill in this diagonal, they need to get this middle term. So when combined, they should add up to a positive 2x. Well, looking at my list of factors, there's only one option that will get me a positive 2x, and that is negative 3 and 5. So I'm going to put negative 3 on one side and 5 on the other. And let's just double check to make sure that we have the correct partial products. Well, negative 3 times x is negative 3x. Negative 3 times 5 really is negative 15. And then lastly, x times 5 is 5x. Reevaluating our diagonals, x squared remains x squared. Negative 3x combined with 5x's will get me 2x. And negative 15 remains a like term of negative 15. So this shows us that x squared plus 2x minus 15 is the product of the quantity of x minus 3 times x plus 5. So it's very interesting to see how Eureka Math builds on itself throughout the story of units as well as the story of functions. Let's take another look. So first we start off with a rectangular array, building our students' foundation on using an area model to multiply just common numbers. Then we get into Algebra 1, or we move into a story of functions, where we're using that same model, but now we are multiplying polynomials. So really reinforcing that idea of the distributive property. Once our students have learned that, well, now we are in Algebra 2, so towards the end of a story of functions, where we're working backwards. We start with our final product, and we want to find the factors. And here you have the coherence of Eureka Math.